Hi, everybody. Welcome to Byte Ventures, where we deep dive into the world of technology. In today's episode, we'll deep dive into Kafka, a distributed messaging system for log processing. We'll talk about what led to the creation of Kafka by LinkedIn in the first place, what were the challenges with the existing systems, and what are some of the design decisions that were taken by the team Kafka that made it fast, popular, and highly scalable. So, without further ado, let's dive deep in. So, before Kafka, what was the situation? Why the situation necessitated the creation of a new tool like Kafka. So, in a decent internet sized company, there were huge amounts of logs that are getting generated. It can be user activities or clicks, like the different parts of the website or a digital product the user is exploring. We want to keep track of that for better functions. And there were a bunch of service operations or monitoring, like call latencies, memory or CPU usages, disk utilizations across different services, and stuff like that. This has become much more important in the recent years because the users expect better recommendations and the targeted ads from the ad agencies. The security applications or the companies use this kind of tool to build their models to make the applications much more secure. But the main challenge is the scale because these data are much higher than the real data in the application or the real user data. So the existing system faced humongous scale challenges. So LinkedIn faced a lot of these difficulties and it thought like, why can't we create something which is a combination of a log aggregator as well as a messaging system? And that is how Kafka was born. Let's talk about the pain points of the existing systems. The existing messaging systems focused a lot on the delivery guarantees because of the way the system has been built in. They were like, oh, if a message is passed into the system, it has to get delivered without any further guarantees. So that was the basic guarantee that all of these messaging systems offered. That led to a complicated API and the implementation. But in case of logs or events, we don't mind losing a couple of click events or view events in a millions or thousands of events, right? So we can relax that a little bit. So the existing system did not support our use cases. The existing system didn't care much about the throughput because these are some of the systems which are built since quite some time. So the scale has not been that huge back then. And the attention of the engineers who developed these products was not on throughput. On the similar note, there was no distributed support as well because the scale was not that big when these softwares were built. So it was pretty hard for this existing messaging systems to run across machines because with the current load, we cannot run it across a single machine, and also for availability. The next and the most important thing was the low unconsumed capacity. So, as the systems were messaging systems, they never proved to be a storage system. So, that means the unconsumed capacity was pretty low, and the performance started to get degraded once the unconsumed capacity became higher. That means the consumers were kind of laggy, they didn't have enough resources to consume the message, and in case that happened, the performance of the whole messaging systems lagged a lot. So these were some of the main pain points that Kafka wanted to solve, and it solved them pretty effectively. So let's talk about Kafka then. So what are the different terminologies in Kafka? We'll come across this, but in this slide, we'll provide a little bit of introduction of the different terminologies that Kafka has. The first one is a topic. So topic is a stream of messages of a particular type. So any particular type of messages sent by a producer eventually goes to a topic. So topic is like a bucket where the producer produces their message and a consumer in some way consumes from that topic. Will go, there's a little bit of nuance for the consumer, but for producers, they have to produce into a topic. The producers are the processors or the clients that produce messages into a particular topic. That should be pretty obvious. Let's talk about consumers. So consumers are the processes that consumes the message from a particular topic or partition. So here we are seeing a term called partition. What is partition then? So partition is basically a subdivision of topic. So each topic is further divided into multiple partitions. So think of it like um, one door has multiple doors inside. When you get through that first door, you have multiple different doors to enter through to enter the building. It's kind of that. And the most important of all is the broker. So the broker are the set of servers or the processes which are running in which the published message is getting stored. And the broker, in case of Kafka, does all the heavy lifting. So each broker stores one or more partition. That means each broker is responsible for some part of a topic, and that is done to distribute the load effectively. Because Kafka is made to be a high throughput system right from the beginning. And that is why these were some of the design decisions that were taken to progress to that state. Okay, so the basic terminologies included producer and consumer. So when LinkedIn wanted to build such a system, they were like, okay, the messaging is pretty simple. So someone sends a message into a single place, and a consumer or another process just consumes from that by specifying the topic name. So they wanted the APIs to be pretty clear, pretty short and concise. And that is why they defined the responsibility of producer and consumer pretty effectively. So let's see what a producer does effectively. So producer is responsible for sending a message. So what is a message? So message is a collection of bytes, right? That is not different from any other systems that we have. So this is pretty similar to other systems. Then after a message is selected or after a message is fixed that needs to be sent across, the producer has to select a serialization format. It can be any serialization format um, that can be used, and the message is then serialized in that format and sent over the network. So there were a couple of optimizations that LinkedIn did, for example, like batching messages, because the existing messaging system, when they sent the messages, they had no concept of batching the messages. So even if there was a small message that needs to be delivered, it had to go through a round trip of TCP/IP connection, and that led to a lot of inefficiencies. So the producers was given the ability to batch messages in case they want to send it more than one message at one go. And then effectively that message lands to a topic that we have discussed about. Okay, let's talk about the consumer. So what is a consumer? So consumer is a process that is responsible for consuming the messages from a partition, not from a topic. That is pretty clear. So a consumer always consumes a message from a partition. So you can say that it's from a topic, but if you have to be very specific, then you have to say it as a partition. So each partition is like a queue in layman terms, which has an iterator interface that the consumer iterates on. So it's like there is an iterator. If you have coded in Java, it's like iterator.next, and you call .next on that queue whenever there is any messages that you're expecting. The iterator in this case is unlike the older ones. It never terminates. So it remains blocked. That means if there are no new messages and you call iterator.next, it remains blocked until there is any new messages in the partition of the topic. I hope the producer's consumer clean APIs should make things much more simpler now. Okay, so let's talk about what are some of the design optimizations that were done by Team Kafka that led to support this high scale and high throughput system right from the beginning. The basic thing is the storage architecture, because as a lot of the things are put into a queue, the consumer consumes from a partition, the storage layer needs to be very, very efficient. So the storage layer was made pretty simple. So each partition that we talk about of a topic corresponds to a logical log file. So eventually it's a log file, where a log file is implemented by a set of segment files. That means each segment file roughly around 1 gigs. It's around that size. It is kept in that range so that each partition receives equal amount of load to have that distributed load balancing. Each segment files is basically a 1 GB roughly file, and then whenever a message is produced by a producer, it gets appended to the last segment file. So as we know, append only mode leads for faster writes because it doesn't have to go through find the right place. A sequential write is a basic computer science philosophy that if you want to make writes faster, it has to be append only to a log file. And that is how all these write ahead logs from a database and all this other systems use. The second, the segment files. The segment files have all of the data, but for the consumers to see the data, the segment files need to flush the data into the disk. But it cannot do it every second because a write to disk is pretty expensive and pretty slow as well. So for optimization, what it does is it batches the writes and flushes them in certain intervals. That is configurable, and it has to do it at certain time interval. And that is how once the batch is flushed to the disk, it is visible for consumers to consume the messages from. So this is a pretty big optimization because you are not writing to disk with every single message, and you can batch them and write it to the disk. Is like avoiding micro writes. Another important and unconventional way is the messages that are put into the queue has no message IDs. This looks quite surprising, right? So if any of us have been coming from the data structure background, so we know that it's pretty easy for data structures like array, where we have the IDs and we have the maps, which kind of stores them actual locations or kind of like hash map. But Kafka did it for a pretty reason of simplicity because they didn't want to maintain additional auxiliary data structures that required mapping the data at the message ID to actual location. So they didn't want to manage all of those complications, and hence they told that okay, we'll not even have message IDs. So the IDs of the message is basically the offset in the segment file. For example, if the segment file is like this and one of the messages here, let's say the offset is 0 here in this, let's say this is 1000. So this message will have a message ID which will be equal to the offset ID, in this case will be 1000, and this will be relative to this segment file. It's not like a global one, but it should be the one within this segment file. That is how it is done. And the another interesting thing is, as these are offset, these are always increasing, but never consecutive. It's not like 1000, 1001, 2, and stuff like that. It is actually the new offset is basically the older offset plus the length of the message. So that is how it is pretty simple, easy to manage, no additional auxiliary data structures to manage in this storage layer. I hope this makes sense. Okay, so we'll talk about this, but let's talk about the consumers. So consumers always consumes message sequentially from a partition that we've already talked about, but the more focus is sequentially. So it's like if a consumer consumed a message of this point, then we can pretty surely say that all of the messages at this area is already consumed by the consumer for that specific partition, right? So it should be obvious in that case that okay, once it is done, the before ones should already be done. So how does consumer consume the messages? So as we talked about, um, or we did not yet, but we will. But some of the optimizations of the older system was that it was push based, not pull based. So that led to certain disadvantages in case the consumer was slower to consume, and that would not lead to like higher throughput systems. So for higher throughput system, the consumer needs to pull the messages at its own speed or whatever it is capable of, and then it can reuse that things from there, right? So the consumer always pulls the message sequentially from a partition, and each of the pull or pull requests, I would say, has these two things, which is the first thing is the offset from which to consume the messages, and the second is the size of the bytes to fetch. um, it internally does some kind of batching while pulling to optimize the structure, but it has to specify batch, even if it feels like the consumer consumes one message at a time. But under the hood, it fetches a chunk of messages and processes one by one, right? That's interesting. So now when we talk about the query pattern, as we know that the consumer is in a pull mode, it provides a offset to consume, so it has to be an efficient query based on the offset. That means the broker should be able to figure out the segment file given the offset. That is a basic requirement, right? So what the broker does is broker maintains an internal in-memory index. It's like a regular index sorted in this way. Um, increasingly sorted, and each of these entries is pointing to the start of the message in each of the segment files. That means this is pointing to the first segment file, this will be pointing to the second segment file, this will point to the third segment file, and so on. So whenever there is a offset request that comes from the consumer, so it will be any of this. So it's like it does a binary search, figures out that okay, this is the segment, or this is the offset that the consumer is interested in. It figures out that okay, what is the starting point of the segment, because it can figure out which segment file, right? I hope you understand. So let's say it's 145. Let's take an example that we got like something like 147, right? Oh, 000 is appended in front. So it queries. So we know that, okay, it's somewhere here. That means it has to get this segment file and search in that. So it'll fire the query, it'll land here. Once it figures out the segment file, it will go in that sequentially, because we know that these are generated in sequence or in incremental orders. So once it figures out the segment file, it's pretty easy to read. So that is how it optimizes the read functionality from the consumers, right? So we have talked about the storage simplicity or the storage efficiency. Let's talk about the data transfer, because the processes like brokers, consumers, and producers can lie in different machines. We have to make the data transfer as efficient as possible. So couple of design decisions that Kafka takes to make the data transfer pretty efficient. The first of all is it doesn't have any cache. It relies on the OS's page cache, which it does for a couple of reasons. So first, it avoids double buffering. What that means is that we don't need to store the messages at two places, especially as a cache. One in the OS's cache buffer, and the second is Kafka's buffer. The second and the most important advantage is that in case a broker goes down, we don't need to rebuild the cache because it's part of the OS's cache. So whenever the broker comes up, it'll go and use that cache. So the cache will be warm even if the broker goes down. And the added advantage of that is like as it doesn't have a lot of memory to manage, there is no garbage collector implementation in this case, which makes their system much more efficient. Then we talked about multi-subscriber system, right? So that means a producer can produce a message into a topic, and those can be consumed by different consumers. There's a little bit of nuance we'll cover in the next slide, but for now, just take into account that each message can be consumed multiple times by different consumers. Okay, so how does that work? So how does the read path or the read data that is read by the consumer effectively lands into the socket? So there are like four different steps to the flow of the data, right? So first, the data is read from the storage media or wherever the storage layer is to the OS's page cache. So once the data is brought to OS page cache, then we can talk about the further steps. Then the data page cache is copied into the application buffer, right? Because there's the application or the process that is running that needs to get hold of the copy of the data for doing further processing. Then the application buffer is copied back to the kernel buffer. It is because the kernel buffer needs to have the data to send it to the socket. And that is the fourth step. So these are the typical steps that any of the system having to send data across a network has to do. Like it has to read from the storage layer, move it to the application buffer, copy the application buffer to the kernel buffer again, and then move the kernel buffer to the socket or copy kernel buffer to the socket buffer. But Kafka figured out that this is not an efficient way. They have to go something else, innovate something, and that is how they use the send file system call. So what Kafka does is pretty interesting. So they copy the storage media or the data from the storage media to the OSS page cache. And once the data is copied, they use this send file system call, which is pretty interesting if you guys want to explore it. It copies from page cache of the OS to the socket buffer. So they save these two copies and one system call. And that is how it makes the data transfer much more efficient and leads them to build a high throughput system from the day one. Okay, let's talk about the broker now. So we know that the broker does most of the heavy lifting, right? So it has to manage a lot of states, then it has to coordinate and all stuff. But by design, they have made the broker stateless. What that means is like the broker does not manage state of each consumers. That is much more efficient because independently they can scale up now. So the brokers can scale up, the consumers can scale up, and it is the responsibility of the consumer to let the brokers know that this is the amount of information or this is the amount of offset they have already consumed. For example, let's say this is a broker, right? This is consumer one, this is consumer two, this is consumer three. So the broker does not know how many messages this consumer has consumed, or how many messages this consumer has consumed, or how many messages this consumer has consumed. It is the responsibility of the consumer to notify that, okay, I have consumed till this message, till this message, till this message, right? It has an advantage and a disadvantage. We'll talk about the advantage first. So advantage in this case is the replayability of the consumer. That means of the consumer can go back and start consuming the messages again in case there is any errors on the consumer side, right? Had there been implemented in an opposite way, then as soon as the broker knew that a consumer one has processed all of these messages already, he'll probably drop those messages for that consumer, right? Something like that. So this gives a pretty big replayability to all the consumers. But the added disadvantage that comes to it is the broker unable to know when to delete the messages, right? Because it doesn't have a track of which consumer has what messages consumed. So it is pretty hard for a broker to figure out which messages to drop. That is why they go with the SLA problem or time to live or whatever stuff like that, right? So it maintains a 7-day SLA where each message in that queue is dropped after 7 days. So it gives like a 7-day SLA for the consumers to consume the message. And I think that's a fair estimate because each of these workloads or the consumers should be able to consume the messages, even if it's a huge system, within a week. So I hope that was a pretty interesting design to make much more highly throughput systems. Okay, let's talk about coordination. So now that there are multiple consumers, multiple producers, they're producing into the same topic, the consumers are consuming from the same topic. So there is a big problem of coordination. How does each of the consumers know what to consume, what not to consume, and stuff like that? The first simple thing that it did was producer producing a message to a topic. There are two ways it can land in a different partition. Either the partition can be randomized, that means the topic or the message for a particular topic can land into any specific partition in random, or it can be determined by the partition key and the partition function. So that is pretty simple. So the producer does not have to coordinate among themselves. Oh, where do I need to send the messages in? So they don't need to coordinate among themselves. They just put the message based on the key. It gets to a specific partition or it is randomized to balance the load effectively. The second and most important thing is the consumer groups. The consumer groups, as the name suggests, is a group of consumers which has one or more consumers. The most important thing in each consumer of the consumer group is that each message in a partition is delivered to only one consumer in one group. That is pretty important. So this only and this one group is very, very important. That means each message in a particular partition is only delivered to a single consumer in that consumer group. There can be different consumers across consumer group that can get the same message, but for the same consumer group, there can be only one consumer that can consume the message. That is very important. With that, they removed all of the heavy lifting because now across all the consumers in that consumer group, no coordination is required unless there are some load balancing activities that is done, which is pretty infrequent. So they have gotten rid of this distributed coordination by having consumer groups and restricting each consumers in that consumer group to be a only single place which can receive the message. That is pretty interesting. The next optimization they did is not having any central master node. So in this design of Kafka, there is no central master node which kind of does anything specific. So the consumers coordinate among themselves to do all of this coordination, talking, and all stuff. So that is pretty interesting. Okay, so let's talk about Zookeeper. I think this is a little bit of older information, and it can be that I have referred the original paper, and I have known that they have removed Zookeeper in 0.9 edition. So this is a specific, very interesting section that I wanted to talk about. So Zookeeper was used earlier for doing all of the housekeeping, like addition of removal of brokers or consumers, and everything was put into Zookeeper. So Zookeeper was a basically highly available what do you say configuration service, kind of that. So where all of the different configurations were put in, Zookeeper was responsible for making it highly available for different services to consume that information, right? So in the earlier versions of Kafka, I think before zero point 0.9, Zookeeper was used very extensively. And the most important use cases was the addition removal of brokers or consumers, triggering a rebalance of the nodes, and maintaining offset of each partition, right? So we talked about how this consumers were responsible for maintaining the offset for each partitions, and that were somehow stored in Zookeeper. But now with the K-Raft mode, I think that came up after the zero point 0.9. I'm not pretty sure, but I think I have read it somewhere that it has native support for broker availability now. So K-Raft controller quorum, I'm not going into details because that is out of scope for this video, but we'll cover it in a later video. So the K-Raft controller quorum has a native support for broker availability. It kind of takes care of the availability, spinning of new broker in case one goes down and stuff like that. For triggering rebalance of the consumer across the messages. So for example, if there are much more partitions, we created much more partitions. So the consumer in a consumer group needs to get assigned to different partitions for proper load balancing. And the Kafka's group coordinator and partition assigner handle consumer group membership and partition assignments. So they leverage these topics like consumer offsets, consumer metadata instead of Zookeeper to manage all of the system in the KRaft mode. It's very specific. You need to understand this is the KRaft mode is available after certain specific versions of Kafka, not for all the older Kafka or the initial Kafka that was designed. Offsets are stored in Kafka's internal topic. Instead of having those information in Zookeeper, now they're stored in consumer offsets, and that is all about the distributed coordination. I hope it makes sense. Let me know if you have any questions in this in the comment section. I'll be happy to address all of these questions. Okay, last but not the least, the delivery guarantees. So we talked about this as the beginning point, that this was the major pain point of the existing messaging system, that they kind of guaranteed a very high delivery, they had a very high delivery guarantee, and that led to a lot of inefficiencies in high throughput systems like log aggregator and all stuff. So we might not need that much guarantees in case of a system. That is the first thing. But what does Kafka guarantee? So Kafka guarantees at least one delivery, or at least once delivery, sorry. So what does that mean? That means it can happen that the same message gets delivered a couple of times or more number of times, but it is guaranteed to get delivered once. Because the exact one delivery requires to implement a two-phase commit and distributed transaction kind of that, and that was not available. I haven't checked the latest versions on this, but as soon as the paper was released or the initial versions of the Kafka was released, they never supported the exact one delivery. So if the consumers wanted to have a single message and they want to have it on their own, they can implement the dedupe logic on their side. They can maintain some kind of hashing to process the message and figure out that, okay, if they have processed the message, then drop it and then just move forward. So it should be pretty simple on the consumer side to implement the dedupe logic. Ordering. So Kafka guarantees ordering from a single partition. So when a consumer reads messages from a single partition, Kafka guarantees the messages will be ordered when they're read from a single partition. This is important. When the Kafka consumers are reading from multiple partitions, the ordering is not guaranteed. That is pretty important, right? The third and most important thing, like any other data systems, is to avoid data corruption. So, to avoid data corruption, Kafka stores a CRC or a checksum, which is kind of that. I think most of the people will know about it. It's like um, hash of the exact message stored alongside the message in each log. So in case of any input output error, the broker filters out the message with inconsistent CRC because it knows that there has been something messed up with these messages. It can happen that the right field or the networking connectivity led to some kind of disruption of that message and stuff like that. So this CRC for each message in the log helps discover which are the inconsistent messages, and those are dropped out when the broker filters it out. And the most important thing in this case is the availability. In some cases, if a broker goes down and the messages are not consumed by any of the consumers, then the messages are lost forever. And I don't know about the latest availabilities or latest updates on this, but that was one of the future works that the team was proposing, that they have to make it more reliable in case if the broker goes down, the messages are not lost. So that will be all on this, and I hope you liked the deep dive session. It was a pretty interesting read, even if the paper was a little bit smaller in length, but it was filled with so much design principles, so much optimizations to make it highly scalable system. So let me know what you think about it. I'll attach all of the references in the documentation, and I hope you have a great rest of your day. Thank you.